Hello and welcome to Lecture 20. Now that Coleman has been corralled here with the amazing help of the Greenie, we are now fully ready to start talking about the symplectic canonical transformations. However, before we get to the symplectic canonical transformations, let us take a look at a couple of examples of regular vanilla canonical transformations or perhaps some other flavors. So let us consider a vanilla canonical transformation. So part 1 of lecture 20. So vanilla canonical transformation of the following form. F2 that is equal to the sum over I of little q's times big P's. And from here we're going to get right away that this transformation gives us little p is equal to big P, and big Q is equal to little q. That is, this is an identity transformation. Let's consider example number 2, where we will look at a different flavor, F1, which is little q times big Q. And from here, we're going to get that Pi is equal to capital Qi, and capital Pi is equal to little qi. And this is a switcheroo transformation, so we switched Q and P. Let's consider example 3. In this case, we are going to get that Qi, capital Qi, is equal to Fi of its arguments. And this is just a point transformation. And the little Pi is given by the partial of f with respect to Qi So you can see that this f function is giving us the point transformation of coordinates. F depends on the old coordinates and time and gives us the new coordinates. And the momenta adjust accordingly. It's given by a gradient of f with respect to the old coordinates times the new momentum, which can be rewritten as simply pi dqi old is equal to pi dqi new. Little ones equal to capital ones. Little ones on the left-hand side and capital ones on the right-hand side. We can invert this relation in order to express the capital P's as a function of little p's and q's. And finally, the Hamiltonian is given, as usual, by the old Hamiltonian plus the time derivative of the generating function. In order to make room for it, I'm going to raise this, which is standard in all of these transformations. And consider example 4. In this example, we're going to partially solve the system that has a symmetry. As you can see, the Hamiltonian is given by a function that depends on the two momenta of the particles, times a function that depends on two momenta, times a function that depends only on the difference between the two particle coordinates. So that is a central potential. And let us now try and partially solve this. We can try and use a vanilla transformation with a generating function of this form. F2 is equal to the difference in the two coordinates, q1 minus q2, times the new momentum 1, plus little q2, the old coordinate, times p2, the new momentum. And this generating function will give us the relationship between the new and the old coordinates, as written here. We can now express the Hamiltonian in terms of the new coordinates. So we used to have f of p1, and p1 is equal to capital P1 of p2, whereas p2 is equal to p2 minus p1, plus g of p1, p2, multiplied by h of q1 minus q2, and q1 minus q2 is going to be just h of q1. So in fact, we can fit it over here. As you can see, this expression is cyclic in Q2. Q2 doesn't appear anywhere here. Therefore, the new momentum number 2, or capital P2, is a constant. It's a conserved quantity. As a result, we can express P1 as a function of Q1, the total energy, and the second conserved momentum. Because this is a conserved quantity, and total energy is also a conserved quantity, it means that we can express P1 by inverting this relation in terms of just Q1 and the conserved quantities, the energy and the capital P2, the second new momentum. And we can also verify that indeed P2 is a conserved quantity. It's just the sum of the two momenta, of the first and the second particle, the original momenta. And if we compute the time derivatives of P1 and P2 and sum them up, then we'll be able to find that this will be equal to minus dH dq1 minus dH dq2, and dH dq1 will be exactly the same as dH dq2 apart from the sign change in the derivative. This will be equal to minus g h prime plus g h prime, giving us 0 as a result. This does it for part 1 of lecture 20, and we're going to move on to the next part, where we're going to start symplectic canonical transformations. I'm going to see you there. Hello and welcome to part 2 of lecture 20. We are now starting to talk about symplectic canonical transformations. So we work in the canonical variables Q and P. Let's put them together in one vector and denote this vector as eta. Then the equations of motion in terms of this vector will look like that, where J is a matrix, and it will be clearer what I just did when we expand this. So let us now try and apply our canonical transformation. So we're going to switch variables from eta to psi. So psi is a vector of capital Q, capital P. So far so good? Okay, stay with me. Now what we would need is that in order for the transformation to be canonical, we would need that the psi dot satisfies exactly the same equation. And here we neglect the time dependence for simplicity so that k is equal to h. So now let us try and take this through. So what is going to be psi dot? We can use the chain rule and express psi dot in terms of eta dots, where the prefactors are going to form matrix Mij. So Mij is d psi I d eta j. So in the matrix form, this looks like M matrix times J matrix times dH d eta, right? This is just the same where we substitute M matrix for this transformation, for this Jacobian, and then we expressed eta j dot via a matrix form because the original transformation is canonical. And now we can switch back from eta to psi in the denominator, and because so for that we would need to multiply by the same exact Jacobian, but because eta is in the denominator, we're going to have to multiply it by m, which is transposed, so that the multiplication works out in the index notation. So this is what we're going to get. And this product of three matrices has to equal to matrix J in order for transformation to be canonical, just so that we get psi dot is equal to J times dH d psi. This means that a requirement, a sufficient and necessary requirement for the transformation to be canonical is that the product of m times j times transpose of m has to be equal to this matrix J. So this is known as symplectic condition on the matrix M. And M is known as the symplectic matrix. This condition is necessary and sufficient for the transformation to be canonical. Even for time-dependent transformations, although we didn't strictly derive this for that case. This condition implies the existence of a generating function, f2 for instance. And for many degrees of freedom, we can also write it down in the following way. So eta will be a combination of Q and P pairs for each of the dimensions, and the matrix J will take this form where along the other diagonal we will get the plus and minus identity matrices. We can actually recast this expression in a slightly different way, making use of the fact that J squared is equal to minus 1. So starting with this condition, MJM equal to J, the condition for the transformation to be canonical, we can multiply each side by M tilde times J. So this is what we're going to get. M tilde times J times M times J times M tilde is equal to M tilde times J times J. But this is equal to minus M tilde. And so as a result, we can cancel out M tilde, and we can get that M tilde J M J is equal to minus 1. And we can multiply this on the right by J. And from here, we can get that m tilde jm is equal to j. So you can see that we can rewrite this condition in the other way, where we have swapped m tilde and m. Now we can try and deal with whether the transformation is canonical or not in a more user-friendly and elegant approach of Poisson brackets. And this is precisely what we're going to tackle in 20.3. I'm going to see you right there. Hello, welcome to part 3 of lecture 20. Here, we're going to talk about the long-awaited Poisson brackets. You might have seen Poisson brackets in quantum mechanics. So now let us see what happens here in classical mechanics, where they kind of originate from. Suppose that we have two functions, u and v, of our coordinates q and p. We're going to now write Poisson brackets of u and v. So Poisson brackets of u and v, given the coordinates q and p, so far it will be coordinate specific, then we're going to get rid of this, is given by the partial derivative of u with respect to qi times partial of v with respect to pi minus the reverse, minus du dpi times dv dqi. Of course, the sum over I here is implied. So if you have multiple degrees of freedom, you're going to have multiple contributions to each of these terms from each of the degree of freedom, summed up. We can now write this out in a vector form. Du tilde d eta times j, that matrix that we defined right over there, times dv d eta. And we can see that that's the case by expanding this and getting this back. So for instance, du d eta tilde, that will be the horizontal vector, so a row vector of du dq and du dp, multiplying the j matrix, which is 0, 0 along the diagonal and 1 minus 1 in the off-diagonal terms, times the dv d eta vector, which is dv dq, dv dp column vector. And if we follow this through, we're going to get simply that this is du dq, du dp, multiplying dv dp and minus dv dq, just from this one single minus sign. And that automatically gives us the original. So we have verified using this here that this is indeed the correct way of writing the definition of Poisson brackets in the matrix form. So let us now compute Poisson brackets of our q's and p's. So this is fundamental Poisson bracket. So you can see that if we write down a Poisson bracket of qi and qj, two different coordinates, we're going to get a 0. Because if we plug in qi and qj for u and v, one of them will always give 0 when we take the derivative with respect to the momentum. Remember, q's and p's are independent, so that's how we get a 0. Similarly, we get a 0 when we try to take a Poisson bracket of two different momenta, or even the same momenta. We're going to get a 0 because there will always be partial derivative with respect to q that is going to kill the bracket. Finally, the only two Poisson brackets that are non-zero is the bracket of q and p, and in this case they're only non-zero when they belong to the same degree of freedom. So qj times pk will be equal to delta jk. And how do you see that? Well, let's evaluate the Poisson bracket for qj and pk. If we plug in qj for u, we're going to get dqj over dqi times dpk over dpi. So that will give us delta ij for the first term times delta ik for the second term. And the last term here is actually going to be 0 because we're going to be taking a partial of qj with respect to pi, and q and p are independent. So this term is not going to be present. And so you can see the product of two delta functions is only going to be non-zero when both I and j are equal to each other and I and k equal to each other, or equivalently when j is equal to k. So this product is equal to delta jk. Very similarly, the Poisson bracket of pj and qk is going to be equal to minus jk. And you can see that from the fact that the definition is anti-symmetric. So if we flip u and v, you are going to get the opposite sign. We can write all of these relations down in a matrix form in the following way. Eta comma eta is equal to j. And here we're using a definition for what it means to plug in a vector into Poisson bracket, namely the components of the Poisson bracket LM component is given by the Poisson bracket of eta L times eta M. And all of this is, of course, evaluated with respect to Q and P coordinates. So here we could add eta, here we could add Q and P, and here we could add eta as well. A few notes are in order. First of all, as we already noticed, Poisson brackets are anti-symmetric, so that uv is equal to minus vu. The other relation is less clear. That is u comma vw plus v comma w u plus w uv is equal to 0. And this is known as Jacobi identity. So this is all great, but we still have to carry around the knowledge of the coordinates with respect to which all the partial derivatives are computed inside of the Poisson brackets. And that's not great, right? Because if they depend on the coordinates, that's really confusing. So it turns out that Poisson brackets are invariant with respect to canonical transformations. Let's verify this. For compactness of notation, I will drop the underlines to denote vectors and double underlines to denote matrices. Let me know if you have questions. So what we have written out is, so what we've done here is we wrote out the definition of the Poisson bracket in terms of the matrix notation. So this is just copied here. And now what we can do is we can switch from eta to psi using the M matrix like we've done on the previous slide. And so here what we've done is we've switched from eta to psi, and therefore we would need to multiply by d psi d eta to cancel out psi and get back to eta. So this is just the first term. And the second term behaves in exactly the same way, but because the order is different, we now are multiplying by du d psi m from the right hand side. We actually need to put a tilde just so that this multiplication works out. So we transpose in M to make sure the right indices align and give us the same and give us the right answer. So now we also can notice that mj m tilde is just j, as we've shown on the previous slide. And so that is the requirement that our transformation is canonical. So with that, we can write down that all of this is equal to simply, which is exactly the same bracket, but with different coordinates. And so that means that this is equal to u v under the coordinates psi. That means that indeed all Poisson brackets are invariant under canonical transformations. Or people like to say that all Poisson brackets are canonically invariant. And so Poisson brackets can be used to check whether a transformation is canonical or not, which is precisely what we're going to do in part 4 of this lecture, where I'm going to see you in just a moment. Don't go away. Hello and welcome to part 4 of lecture 20. Here we're going to use the Poisson brackets in order to check whether our transformation is canonical or not. Here is how we're going to do this. We're going to require that the Poisson brackets of coordinates and of momenta are 0, and Poisson brackets of coordinates and momenta are delta function. So that Q and P is equal to 1 only when the index I is equal to the index j, and otherwise, if the indices are different, then the Poisson bracket is going to give you 0. So Q1 P1 will give us 1, and the Poisson bracket of Q2 and P1, for instance, will give you 0. Or similarly, Q1 P2 Poisson bracket will also give you 0. So let us try and look at this for an example of what we did last time for canonical transformations. Let's compute the Poisson brackets. So what we're doing here is we're computing the Poisson brackets using these definitions. So it should be dq1 dqi times dq2 times dpi. And we're plugging in the expressions for Q1 and for Q2 over here. This is only the first term, and the second term will be where we will have switched the order of the indices. And because in both of these cases we have a partial derivative of Q with respect to P, all of this is going to be 0 because such a partial derivative is going to be 0. Similarly, the Poisson brackets of P's with each other are also going to be 0. However, if we compute a Poisson bracket of Q1 P1, then we're going to find that it is not 0. And you can see that this is non-zero only when I is equal to 1. And so we're going to get dq1 minus q2 dq1, that's going to be 1, and dp1 over dp1 is going to be 1. So all of that is going to be 1, just like we would expect for a canonical transformation. Similarly, if we wanted to do q1 p2, so for Q1, P2, we're going to have something more interesting, but still 0. We're going to have dq1 minus q2 over dqi over here, just like here. But here we have P2, so P2 will be P1 plus P2, so capital P2 is equal to the sum of little p's. And you can see that we will have, oh yes, and I also need to include the second term. Which will be minus, with these flipped, dp1 plus p2 dqi times dq1 minus q2 dqi. Oh, dpi. And you can see immediately that this second term is going to be 0 because p's and q's are independent. So this is 0 and that is 0 as well. Now this one is more interesting. So you can see that we can have non-zero values of this term both for I equals 1 and I equals 2. So for I equals 1, we're going to get minus 1 for, sorry, plus 1 for this and plus 1 for that, right? So we're going to have plus 1 for the first value for I equal to 1. And for I equals to 2, we're going to get minus 1 over here and plus 1 over here. So we're going to have minus 1 for I equals to 2. And as a result, we're going to get a 0. So as we expected. Finally, in a very similar way, we can also obtain that the Poisson bracket of Q2 P1 and Q2 P2, both of them are 0. Let us move on to the next part where we're going to use Poisson brackets to compute time derivatives of things, which we will do in part 5 of our lecture 20. And I'm going to see you there. Hello and welcome to part 5 of our amazing lecture 20. We have just discussed canonical transformations and Poisson brackets, so now let us try and see what we can do with Poisson brackets. Can we do something useful with them? It turns out, yes, we can. Namely, what we can do is we can use it to operate on functions. Let's see how that works. Suppose that we would like to compute a time derivative of some function of q, p, and t. Just like that. So let us use the chain rule. Qi dot is equal to dh dpi, and pi dot is equal to minus dh dqi. What this means is that this is a Poisson bracket of u and h. Namely, what we're getting is du dt is equal to the Poisson bracket of u with h plus the partial time derivative of u with respect to time. So this means we can think of h operating on u. There are a few awesome consequences to this. Suppose that u is equal to q. You can see that Q dot is given by the Poisson bracket of Q with H, and because Q doesn't explicitly depend on time, this is just equal to dH to P. Looks like we're getting our canonical equations back. Finally, if U is equal to H, then we're getting that the full time derivative of H with respect to T is equal to its partial derivative, because Poisson bracket of H with H is 0, because Poisson bracket is antisymmetric. This is really important. This shows that the Hamiltonian is a conserved quantity if it doesn't explicitly depend on time. This is important because it shows that if Hamiltonian doesn't explicitly depend on time, so the partial derivative of H with respect to T is 0, that means that Hamiltonian is going to be conserved. So suppose that the Poisson bracket of U and H is 0. For U, that is a function of coordinates and momenta. Then U is going to be constant motion. And why is that? Well, if we plug it in here, you can see if U, comma H is 0 and U doesn't explicitly depend on time, then the full time derivative of U has to vanish, or it is conserved. Finally, a really curious observation is that if U and V are both constants of motion, then their Poisson bracket is also going to be constant of motion. So, how can we show that? Well, let's use the Jacobi identity. You can see that V and H would have a 0 Poisson bracket. U and H is going to have a 0 Poisson bracket. And so therefore, U and UV Poisson bracket with H will also be 0. Which is precisely what we set out to show. That means that U, comma V Poisson bracket is a constant of motion. Let us now consider a couple of examples that will help us illustrate these concepts. And we're going to do this in the last part of lecture 20, part 6, where I'm going to see you in just a moment. So let us consider a couple of examples, and this is part 6 of lecture 20. Example number 1 of how we can use the properties of Poisson brackets that we have just derived. Suppose that both x and y angular momenta are conserved in some mechanical system. Can we compute a third conserved quantity? Sure. The Poisson bracket of Lx and Ly will give us a third conserved quantity. So what will this quantity be? Let's take a look at it. Lx is ypz minus zpy, and Ly is zpx minus xpz. And this is going to be ddxi of ypz minus zpy. So far, all we've done is we simply used the definition of Poisson bracket, and we used xi and pi as the canonical variables. And what we can see here is that the only possibility for anything here to survive within this term is to take a derivative with respect to either y or z. And here, for this term to be non-zero, the partial derivative should be either with respect to x or px or pz. So you can see the only way for both of these not to be zero is when this partial derivative is d dz and this one is d dpz. So this is what we get from the first term. And then the second term is going to be rather similar. Let's take a look here. So here, the only way this partial derivative is non-zero is if we take a partial derivative either with respect to z or x. And this one is whether if we take partial derivative with respect to pz or py. So it's again the same exact story. In order for the product to be non-zero, both of them have to be non-zero, and therefore the only way is for us to consider d dz and d dpz. So d dz of this will be px, and d dpz of this will be y. And this is going to give us nothing but lz. X times py minus y times px. So what we've found is that if both x and y angular momenta are conserved, their Poisson bracket will give us Lz, the third angular momentum, which also will be a conserved quantity. Let us consider yet another example. Suppose that our Hamiltonian for a two-dimensional system does not depend on Q2. So H is equal to and it does not depend on Q2. From here, we know that P2, H will be 0, and therefore P2 will be conserved. Let's consider example number 3. What happens if our H is and is given by some function of two momenta and phi, which is given by alpha q1 minus beta q2. In this case, one can show that p1 comma h is equal to minus df d phi times alpha. p2 comma h is equal to df d phi times beta, And from here, we see that P1 divided by alpha plus P2 divided by beta is constant. The Poisson bracket of this with H would be 0, but therefore the quantity itself is a constant or a conserved quantity. With these out of the way, we can get started on Hamilton-Jacobi equations in lecture 21, where I'm going to see you. Bye.